And chapter 10 about tree. Let's go through it really quick. If we scroll down, we see the introduction. We have already read about various linear data structures like array. They are linear. Linked list. They are linear. Stack and queue. Both array and linked list have a drawback of linear time required for searching an element. So the weakness in linear data types is the searching time. A tree is a non-linear data structure which is used to represent a hierarchical relationships. This hierarchical means parent-child, like hierarchy, like levels, all right? Each node is connected by another node by directed edges. So tree in organization, we have the hierarchy in organization, and tree in a file system it's like that. In the file system, we have the root, the C, and we have the Windows folder and the program files folder, and each one has subfolders and so on. Terminology in a tree, right? Let's talk about some terms. The root of a tree is the only node in the tree that has no incoming edges. It's the top node of the tree. Node, it's a fundamental element of a tree. Each node has data and two pointers that may point to null or its childs. If it's at the end here, then it points to null, which means it's the last one. Otherwise, it will have childs. Edge, it is also a fundamental part of a tree which is used to connect two nodes. These links that can be directed or not directed, they connect the two nodes. For example, this link here, this edge, connects node 4 and node 2, right? Path is an ordered list of nodes that are connected by edges. So the path from root to 1 is this one. This is the path. All right. A leaf, just like a leaf in a tree. A leaf node is the node that has no children, like it's at the very edge. It's a leaf, right? Height of the tree. The height of the tree is the number of edges in the longest path between the root and the leaf. So the height, like how tall it is the longest path. So height equals the depth and equals 4. Why? Because it has 4 nodes. 1, 2, 3, 4. This is the longest path, and this is the height of this tree, right? The level of node. The level of node. The level of node is the number of edges on the path from the root node to that node. The level of node. So this is level 1. The root is 5, right? This level 1, level 2, level 3. So number 1 node is level 3 node, right? All right. Level 0, level 1, level 2, level 3, just like that. Parent child, these are siblings, yeah. Children nodes have incoming ages from the same node to be said to be the children of that node. Parent node is a parent of all the children of the child nodes that are linked by outgoing ages. Siblings nodes in the tree that are children of the same parent are said to be siblings, like brothers and sisters. Ancestors, a node reachable by repeated moving from a child to a parent. Ancestors. Now we are done with the terminology. We'll talk about the binary tree. A binary tree is a type tree in which each node has most two children. At most two children. So it has either 0 child or 1 or 2. Maximum 2 children. This is called binary, which are referred to as the left child and the right child. So each one has 2 children, left and right. Below is a node of the binary tree with a stored data and whose left child, L child, and whose right child, R child, both pointing toward null. All right. So this is just one element of the binary tree, and both are pointing to null. It's not pointing to anything. It doesn't have any children, doesn't have parents, right? And we have the two, left and right. Below is the class definition used to define node. So here is a class, we name it tree, and it includes private and public elements inside it, just like that. And here's the constructor, which is here. Sorry, here's the method, which is here. And here's the constructor. Below is a binary tree whose nodes contains data from 1 to 10. And the rest of the book, binary tree, will be represented as below. So when we, in the rest of the book, now we are page 299. Until the end of the book, 585, the binary tree will be represented as shown in this figure. Properties of binary tree are the maximum number of nodes on the level I of a binary tree is 2 to the power of I, where I equals and greater than 1. The maximum number of nodes in a binary tree of depth k is 2 to the power k plus 1, where k equals and greater than 1. There is exactly one path from the root to any node in any tree, just one path. A tree with n nodes have exactly n minus 1 edges connecting these nodes. The height of a complete binary tree of n node is log to the base 2 log n, where n is the number of nodes. Now let's talk about types of binary trees. The first type is complete binary tree. In a complete binary tree, every level except the last one is completely filled, is fully filled, except the last one. All nodes in the left and right are filled first, then All nodes in the left are filled first, then the right one. A binary heap is an example of a complete binary tree. So it's fully filled except the last level. Full strictly binary tree. Another type of binary tree is full strictly binary tree. The full binary tree is a binary tree in which each node has exactly 0 or 2 children. Each node has 0 or 2. So this one in the top here has 2. This one has 2. This has 0. This has 0. This has 0. So this is called full strictly. All right. Perfect binary tree. The perfect binary tree is a type of full binary tree. All right, full, just like this one here, 0 or 2, in which each non-leaf node has exactly 2 children nodes. So this is perfect. All leaf nodes have identical path, length, and all possible node slots are occupied. So this is how to be perfect binary tree. Right-skewed binary tree, and this is the perfect one, right? Right-skewed binary tree, a binary tree in which either each node is having only one right child or no child, is called right-skewed. Skewed to the right or skewed to the left, just like that. Height-balanced binary tree. A height-balanced binary tree is a binary tree such that the left and right subtrees for any given node differ in height by max 1. So it's balanced. Each complete binary tree is a height-balanced binary tree. The rule says each complete binary tree is a height-balanced binary tree. What's the height-balanced binary tree? A height-balanced binary tree is a binary tree such that the left and right subtrees for any given node differ in height by max 1. Just maximum 1, all right? Different height. This is called what? Height balanced. AVL tree and RB tree are an example of height balanced tree. We will discuss these trees in advanced tree topics. Problems in binary trees. Create a binary tree given a list of values in an array. And here's the solution. All right. Level order binary tree. And here's the complexity analysis. Pre-order traversal. Traversal is a process of visiting each node in a tree. Traverse through them. Like go through them. In a pre-order traversal, parent is visited traverse first, then left child, then and right child. Pre-order traversal is a type of depth-first traversal. So we go from 6, then we go to all the left ones, then go to all the right ones, then move to the number 8 here, then go to the left ones, then the right ones, and this is traversal. All right. Post-order traversal. Post-order traversal, left child is visited, traverse first, then right child, and last parent. So we start with the left, then we move to the right, and at the final, we go to the root of the tree or the parent. This is called post-order. All right. So in the post-order, we start from left, right, then parent. From the pre-order, we go from the parent, left and right. Pre-order traversal is just like this, as shown in the figure. Post-order traversal goes like this. It starts from child, left, right, then at the very end is the root. All right. In order traversal, left child is visited, traverse first, then the parent, and last right child. So it's a sequence, either root, then parent, left, then right. We call it pre-post traversal, or it's left, right, then parent. We call post, or it says in order traversal. We call it in order traversal, where's the left parent then right, left parent then right, left parent then right, just shown here. So just the sequence, right? Level order traversal, breathe first traversal, breath first, right? Write a code to implement level order traversal of a tree, such as the. So it's by levels. This is the first level, second level, third, fourth. Yeah. Print birth first, right? Print depth first without using recursion. Right? Tree depth. Tree depth. Depth is tree is calculated. Depth is tree is calculated recursively by traversing left and right child of the root at each level of traverse. Depth of left child is calculated and the depth of right child is calculated. The greater depth among the left and right child is added by 1, and this value is returned. And here's the tree depth. Nth pre-order, we get that. We want to print the node that will be at the ninth index. When we print the tree in the pre-order traversal, we keep a counter to keep track of the index. So we have a counter that refers to the index. When the counter is equal to index, then we print the value and return the nth pre-order index node. And here's the code that prints the nth pre-order. Nth post-order, here's the code for that. Nth in order, here's the code for that. Right? Pre, post, and in, different ways. Parent, left and right, left, right, and parent, left, parent, and right. Copy tree. Copy tree is done by copy nodes of the input tree at each level of the traversal. of the tree. At each level of the traversal of node 3, a new node is created and the value of the input tree is copied to it. The left child tree is copied recursively, and then pointer to new subtree is returned with the assigned to the left child of the current new node. And here's the code for the copy tree. Copy and mirror tree. Mirror it. Make it like a mirror. Switch between the left and right. Copy mirror image of the tree is done same as copy, but in place of left child pointing to the tree formed by the left child traversal of an input tree, this time left child points to the tree formed by right child traversal. This is the only difference. And here's the code to print a mirror, copy mirror tree. Number of elements, number of nodes at the right child, and the number of nodes at the left child is added by 1. And we get the total number of nodes in any tree subtree. Why we add 1? Because of the parent. So we calculate all the left and all the rights, and we add 1. Number of leaf nodes. If we add the number of leaf nodes in the right child and the number of leaf nodes in the left child, we will get the total number of leaf nodes in the tree, in any tree or subtree. Leaf nodes that doesn't have children, right? Identical. Two trees have identical values if at each level the value is equal. So check these trees is equal, tree 1 and tree 2, right? Free tree. The tree's traverse and the nose of the tree is freed in such a manner such that all the children nodes are freed before it. So the start from children goes up to the parents and free them. Just delete, all right. Tree to list, Rick. Tree to list is done recursively. At each node, we will suppose that the tree to list function will do its job from the left children and right children, then we'll combine the result of the left-hand child traversal. We need a head and tail pointers of the left list and the right list to combine them with the current node. In the process of integration to the current node will be added the tail on left will be added to the tail of the left list, and the current node will be added to the head to the right list. Head of the left list will become the head of the newly formed list, and tail of the right list will become the tail of the newly created list. And here's the tree to list recursive. Here's the code for it. Here's the code. All right. Print all paths. Print all paths from the root to the leaf. And here's the function that does that, or the method. Least common ancestor. We recursively traverse the nodes of a binary tree. We find any of the nodes are searching For then we return that node, and we get both the left and right at some valid pointer location other than null. We'll return that node as the common ancestor. This common ancestor. And here is the code for the least common ancestor for reference, and here's the rest of it. So when you need it, you find it, and here is the full thing. Find max in binary tree. Find max to find the maximum value in a binary tree. Find max BT method. Here's the code that does that. Here's the rest, right? Search value in a binary tree. So you have a value and a pointer to the tree, and you start searching, and here's the method that does that for you. You go through them, right? Max depth in a binary tree. Here's the method that does that for you. Number of full nodes in binary tree. The number of full nodes. A full node is a node which have both left and right children. All right. Maximum length path in a binary tree. Diameter of a binary tree. Maximum length path. This method shows the maximum length. Sum of all nodes in a binary tree, right? Here is the method that sum all of them. Iterative pre-order. Here is the method that does that. Iterative post-order. Of course, iterative in order. And binary search tree, BST. A binary search tree is a binary tree in which nodes are ordered in the following way. The key in the left subtree is less than the key in its parent node. The key in the right subtree is greater than the key in its parent node. No duplicate key allowed. So it doesn't allow duplication, and it sort them. On the left is the smallest, on the right is the highest. That's shown here. So we have 6, 4, 2, and 5, 2, 1, and 3, yeah, just like that. 8, 7, and 9, 9, we have only 10. What are the problems in binary search tree, BST? All binary search tree algorithms are valid for binary search tree too. All BST, binary tree algorithms, all the algorithms for the binary tree are valid for the BST, right? Create a binary search tree for sorted array. How to create, we have a sorted array, we would like to create a binary search tree, BST. We do that by this one here. Insertion. Below are the steps. Below step-by-step tree after inserting node in the order. Yeah, just like that. 6, then 6, 4, then 6, 4, and 2, and 6, 4, 2, and 5, then 6, 4, 2, and 1, and 5, and 5 first, then 1, then we have 6, 4, 2, 5, 1, 3, just like that. So we start from the left, then right, then the left of the child, then the right, and we keep going on. Insert node. All right. Finding a node, we have the value and we try to find a node. It's done like this by using this method. This is the find method. All right. And to find the minimum, we use this method. And to find the maximum, we use this. And to check is tree is binary search tree. This is the method that checks that. All right. Here's an example. To delete a node, we follow these steps. All right. And here is an example of deleting a node. Least common ancestor, LCA, and the binary search trees. Trim the tree nodes which are outside range. Given a range as minimum maximum, we need to delete all nodes of the tree that are out of this range. Trim it, cut them, right? And here we do the trim outside range. Print tree nodes which are in range. This is how we print them. Find seal and floor values inside binary search tree given key. Given a tree and value, we need to find the seal value of the node in the tree, which is smaller than a given value. I need to find the floor value of a node in tree, which is bigger. Or aim to find the seal and floor values as close as possible than the given value. So the seal and the floor are the highest and the highest and the smallest that are really close to the value, the closest, like the next and the previous, right? Here's the code, and we have the chapter exercises. More exercises, more exercises. so many exercises. This is like really rich chapter, full of details, full of methods, full of exercises. It's about tree. To go in depth through that, probably 3 months is required. Right? We are done with the exercises, and in the next video we'll skim or browse the priority queue, chapter 11.